Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. A little bit about OneClass and what we're doing here. We're very fortunate to have, to modify kind of our resources to be, to deliver online teaching. And we're at OneClass we're actually very, very thankful for this quick transition that we're doing. And what we're doing here is we're throughout this journey, we are currently verifying solutions to frequently asked questions in math and in chemistry. So this can kind of contain in the secondary school level, ranges between the secondary school level and also in the university level as well. So currently what I have for us today is I have about 10 kind of grade 11, grade 12 chemistry questions for us to do for today. And you'll be able to follow along in the chat. And if you have any questions, you can definitely just wave hi or just ask me in the chat. Again, my name is Joey. I'm currently an Ontario school secondary school educator. My teachable subjects are indeed chemistry, and I'm soon getting my mathematics teachable as well. So without further ado, let's get started on these problems here. Okay, so first question is asking how many monochloro substitution products are produced when the alkanes below are chlorinated. So this is question one. Question one. And I have two kind of two kind of compounds here. So this is 1A, I guess. So 1A, I'm gonna draw this out, and then I'm going to basically chlorinate it. And I'm specifically looking for a monochloro substitution. So I'm gonna react it with monochloro compound here, so HCl, and it's asking us how many number of substituted products are there. So where can this where can the Cl minus bind? So let's look at how many places it can bind at. So it can bind here. Maybe this here is 1, this here is carbon 1, this here is 2, and this is 3 and 4 carbons, right? However, if I were to draw out these four structures, and I'll draw that out close. I'll draw that out quite quickly. So, for example, one of these HCl's could be here. So that's one possibility. Our second possibility could be here. Our third could be here, and our fourth could be here, right? And then if I realize specifically with these two compounds here, so this one, so these guys here, they're actually the same compound, right? If I flip if I flip it this way, I would actually get the same compound. I would get back this as well. So this is actually the same, which means I can't count this as another compound here. So it means in this case here, I'm going to have the number of monochloro substitution products are indeed 3 here, because I have here, this is 1. Sorry, excuse me. This here is number 1. This here is 2, and this here is 3. So these are going to be my 3 monochloro substitution products for number A. And then for B here, for 1B, what can I do here? For 1B, I have this structure here, and then I'm going to again undergo a chlorination, and let's see how many products I can produce. Again, in this case, I have 5. Actually, I have 6, right? I have this is carbon 1, 2, 3, 4, 5, and 6. I have 6 spots where I can chlorinate it, but again, some of them might be a repeat structure like we saw in the previous question. So let me draw out the first one here. So that's number 1. Number 2, I'm going to write a chlorine here. So maybe I'll do 1, 2, 3, 4, 5, and then chlorine could go over here. And then if you realize, if I did it to the other side as well, to this side and this side, they're actually the same compound as 1 and 2 here. So I'm not going to cover these carbons here. This is carbon 1, this is carbon 2. Carbon 3 would be, I would have something that looks like this. Carbon 3 here. This here would be the third kind of product here. And finally, I could have it on this last carbon here, and this would be our 4th product here. So 1, 2, 3, 4, 5, and this would be another Cl here, and this one would be our 4th product. So, and as I said before, if you chlorinate between these 2 spots as well, they're going to be the same thing as this first product. So if I draw this out, and Cl here, this is exactly the same. If I flip this 180 degrees here, this one would be the exact same as this compound here. So I don't count this one, nor do I count this one as well, because this one, if I flipped 80 degrees, it's the same thing as this guy here. So I don't count these two products as well, because they're the same as 1 and 2. So therefore, in total, I'm going to have 4 compounds for this guy here, and I'm going to have 3 compounds for this guy here. So let's look at the answer here. Again, 3 and 4, which is correct. So 3 compounds, and they drew out 1, 2, and 3, which is great. And then 4 compounds, and they drew out 1, 2, 3, and 4, which is also great as well. So the solution here is correct. It's correct. Good analysis as well. Okay, let's draw out this structure here. This is 2A, or number 2, sorry, number 2. So it says, draw the product of the hydrogenation of cis-2-pentene. Draw all hydrogen atoms. So I have a double bond here. I have H here, H here. This is a methane group here and a ethyl group, methyl and ethyl. I'm going to react it with or plus H2. I'm going to write vertically and a palladium catalyst here. What it's going to do is actually going to add hydrogens to this double bond here, right? I'm not going to draw the mechanism because it's actually quite complicated for a hydrogenation reaction, but it's actually going to break this. It's going to hydrogenate this double bond, and it's going to make it into a single bond. So I'm going to be left with this guy here. So I'm going to have 1, 2, 3, and then this here is going to be a single bond. I'm going to have a hydrogen here and a hydrogen, or sorry, I'm going to have a hydrogen here, a hydrogen here, and a hydrogen and my methyl group like so, and then same thing for this guy here. So actually, let me draw this out like better, because I don't really like this guy here. Let me see. I have my H here, and my H3C. And then I'm going to have H here, and then my ethyl group. So this is CH2, CH3. Or if you were to be, if I were to draw it nicer, I would actually just get rid of these hydrogen bonds. Oh, sorry, there's a hydrogen here. And I'm going to do 1, 2, 3. So I would have 1, 2, 3, 4, 5. It would actually just be a pentane that looks like this. So this here is actually a much better drawing than this guy here, because this doesn't represent the geometry of this problem here. So it just actually becomes pentane if I hydrogenate cis-2-pentene. And as you can see, this solution here is correct, right? Again, I have 2 hydrogens here, H3C is bonded to this. I have 2 hydrogens, and then I have CH2, CH3 here. So this is actually correct, because they actually wanted us to draw the hydrogen atom, so here we go. So the solution here is correct. It's a good analysis as well. So again, the hydrogenation reaction is simply just an alkene headed towards an alkane. I'm hydrogenating, I'm saturating the double bond there with the hydrogens. Okay, let's look at this problem here. Let's indicate the order of a reaction consistent with each observation. So this solution doesn't really tell us anything here, but I'll read that for us as well. So this is number 3, right? Number 3 is asking, indicate the order of reaction consistent with each observation. This is A here, the half-life. So let me write this, the half-life of the reaction. I'm going to use RxN for reaction, the reaction. Reaction gets shorter. Gets shorter as the initial concentration is increased. B is stating a plot of natural log of the concentration of the reactant versus time yields a straight line. Oh, line. C here is the half of the reaction, the half-life, sorry. The half-life of the reaction RxN gets longer as the initial concentration is increased. So that's going to indicate the order of reaction consistent with each observation. So let's look at these observations first. So the first guy here says that the half-life of the reaction gets shorter as the initial concentration is increased. So if I'm increasing the concentration of the initial concentration here, the half-life is getting shorter, right? So you can think of this as, remember our rate of reaction, right? So you can think of the rate of reaction here. It would be R would equal, and I would have the products, right? So R would equal, let's say here, X times some Y here. And we want to know, or actually I have a constant here. This is K times X times some Y here. And this here's the rate of reaction. And this is the equation for the rate of reaction, right? So it's asking us if we increase the initial concentration here, the half-life is going to get shorter, or you can say the rate here, it's gonna get smaller, right? So if that's the case here, it's definitely a non-linear. It's a non-linear order, so it can't be first order. But in this case, it would be the second order, right? Because again, if it's half-life, for example, if it actually gets halved, if it gets shorter, if I'm increasing X here, my rate here is going to get shorter here. So this first guy here is a second order, right? So this here would be a second order reaction. B here is asking us a plot of natural logarithm of the concentration of the product versus time yields a straight line. If it yields a straight line here, it means it's linear, right? So therefore, this would be rate would equal X here, and then this would be the first order here. So this is first order, and we can actually do a graph here, right? So we can say, we can plot here, just a small plot here. It says a plot of the natural logarithm of the concentration. Oh, sorry, not these lines here. I want so it says the plot of natural logarithm of concentration versus time, right? So this here would be, you can say this is ln X here. So this guy's ln, this guy is ln X, and this here is T. And as you can see, it's going to be a straight line. Like it can be a straight line going, I should probably use my line tool here. It's going to be straight down here, right? So this here would be a first order type of reaction here. Finally, C is stating here the half-life of the reaction gets longer, so it doesn't get shorter, it gets longer here as the initial concentration is increased. So if this was second order, this is first order, this one would be 0th order, right? So 0th order, because it doesn't matter, it doesn't matter what my initial concentration is, independent of the initial concentration. So this is a 0 order reaction. This would be R simply equals K, this X to the 0 here. So this here is simply just 1. So R here equals the constant simply. So this here is my solution for this problem, and this analysis here is correct as well. So solution is correct. Analysis. This is kind of like 3 questions in one again, so might be a bit harder here. That's number 3. Number 4 is asking us, use the periodic table to determine each quantity. Okay. So I care about, this is a 4-part question. Okay, so this is number 4. A is asking us, I want the number of 3s electrons. I'm going to use E- electrons in magnesium. B here is number of 3d electrons in, this is chromium, and C here is number of 4d electrons in yttrium, or in Y, and D here is number of OP. What's OP electrons here? I think it's asking us for, I'm looking at the answer here. I think it's asking for 6p here. So let me say 6p in lead here. Okay, so Let's look at the first one here. Number of 3s electrons in magnesium. I go all the way to magnesium here. I could write out my electron configuration for magnesium. So it'd be 1s2, 2s2, 2p6, and this here is 3s and then 2 here. So in this case here, I'm going to have 2 electrons here in my 3s orbital, right? So I want the number of 3s electrons in magnesium. This here, my answer here would be 2, right? This here would be 2, because you can think of magnesium having, this is 1s2, 2s2, 2p6, and then it's 3s2 here. And 3s2 is going to determine my number of electrons here is 2 here. So I'm going to have 2 electrons in my 3s orbital. In chromium, chromium is 24, number 24 here. So again, I can write out my electron configuration as well for chromium. So it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then I would have 4s2 here, it would be here, and then I have 1, 2, 3, 4, right? So this would be a 3D 10 block, so this is 3D and 4. Which means my number of electrons here is going to be, I have 4 electrons in my 3D block, right? So it's going to be 4 electrons here. So again, this is writing, this here says the number of electrons at 3s is 2, which is good. The number of chromium electrons is 5. Oh, they have 5 here, not 4. Why is that? 1, 2, 3, 4. It should be 4. 5 would be manganese here. So in the 3D block, it's actually this. So this solution here is incorrect. This here is actually a 4 here. Let's look at the other one here. So we have yttrium, which is Y here. That's all the way here. So I'm going to write down my electron configuration for this one here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. This is 4p6, 5s2, and then we have 4d, and then 4d. My d, I want my d of 4d electrons. I have 4d here. This is simply just 1, right? So this here is the first electron here. So this is 4d1. So therefore, my electron here is simply just 1. Right? I have 1 4d electron in this case. In this case, they got the solution right here. And finally, in PB, PB is all the way down here. It's asking us the 6s2 electrons. I'm not going to write the configuration because it's pretty long here. But if I want the 6, this here is a 6p, oh sorry, this is a 6p orbital. Here, the p orbital starts again at, it starts at thallium here. So this is 1p, this is 2p, sorry, this is 2p, 3p, 4p, 5p, and this here is 6p, right? So 6p1, this here is 6p2, so therefore I have 2 6p electrons, right? So I have PB here is basically everything, and then it will have 6p and then 2 here, so which means I have 2 electrons in 6p, right? Thallium is 6p1, lead would be 6p2 here. So this solution here is correct, is partly correct. C here is, oh no, B is incorrect. And why did we say B was incorrect? Well, we said there's 4 electrons here, right? So the So I'm saying here the electron configuration of CR is as follows, and I'm going to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d and 4. Therefore, there are 4 3d electrons. 3 electrons in CR. So A, C, D are correct. So for this case, I'm just going to write it incorrect just so I can correct question. This is question B here. So I'm going to write incorrect here just to correct part B here. Okay, that's question 4. So I got 5 here. 5 here is asking us which of the following is the aqueous net ionic equation for the reaction of NH3 with HCl. Okay, so I want the net ionic equation. Sorry, net ionic equation. And I want, it's NH3 with HCl, right? So let me write NH3 here. So I have NH3. This is an aqueous solution plus HCl, also an aqueous solution. And what am I going to get after I add this? So again, this here is this ammonia, I know, is a weak base. And you can search up the pKb. Kb, I believe it's 1.8 times 10 to the negative 5. You might have, don't quote me on that one, but I believe it's something like that. And then this here is a strong acid. HCl is a strong acid. So this here is, obviously, it's going to be in equilibrium, right? Weak base, strong acid titration. It's going to be in an equilibrium position, equilibrium kind of reaction here. And then I'm going to get kind of this reaction here. It's going to be in the equilibrium. And I'm going to get, again, this HCl is going to be a hydrogen donor, right? So I'm going to get, this here would be NH4 plus Cl minus. And this here is going to be my ammonium and my Cl minus product. And these are my products in this case here. And then it's also saying, but I want, in this case, I want the, again, net ionic equation, right? So I can also look at these guys here, and I can also dissociate them, right? So these guys can also react with water, right? So let me write down those guys here as well. So NH3 AQ I can react that with water, and water in this case would behave as an acid. So I get NH4 plus OH minus. And the HCl obviously can react with water, and this is actually just a fully dissociation because it's a strong acid. This would give me H3O plus Cl minus here. So again, these guys also are also in play when we're talking about this kind of reaction here. But again, it's asking us which of the following is the aqueous net ionic equation, right? So I'm looking at which one will give us our equation here as well. So what we have to do is, we're basically going to break these guys down into its kind of a cation form, and then we'll be able to figure out our net ionic equation here. So let me look at the solution here, and let me see if they're following my thing here. So again, net ionic equation, HCl, NH3 is just the following. So the reaction is only arrow to the right here. So it says NH3 plus H plus Cl would give me NH4 plus Cl minus. So again, this here would be this solution here, this top one is good, right? Because again, I have NH4 plus and Cl minus here, and these guys here are aqueous solutions, right? So in this case here, what we have here is we can actually replace this HCl with our H3O plus, right? So again, H plus can be replaced, right? So let me write that down for you. So let me erase these guys here. Ivan says hi. I'll say hi back. Hello. Thanks for tuning in. So again, NH3 and HCl, and I have ammonium and my chloride ion here. So in this case, this here is asking us. It's asking us, this is number one, right? So here we have, you can actually rewrite this as, what they did was they actually dissociated this, because this dissociates fully, right? So AQ plus H plus AQ plus Cl minus AQ, and this reacts to form NH4 plus. NH4 plus Cl minus, and I can add also water here as well. And what I can do here now is I can actually replace this H plus with H3O plus, right? Because I know that this here is, they're synonymous. So I can say this here is H3O plus. And right now what we can do is we can cross out some common ions, right? So again, I see Cl minus is here and Cl minus here. So these guys are, they don't contribute to our net ionic equation. So therefore I can rewrite my net ionic equation as NH3AQ plus H3O plus is going to react to form, this is NH4, so ammonium plus our water here. And this here is or I guess this is in liquid form, sorry. And this here is our net ionic equation for 1 here. Because I can simply just cross out this chlorine ion or chloride or chloride ion here, and this here will be our net ionic equation for 1A. And then part B is asking us the reaction that occurs when NH4Br dissolves in water. So let me write that down for you. So I have NH4 NH4Br when it dissolves in water, right? So this is actually going to dissolve firstly to, I have NH4 plus or ammonium plus our Br minus here. So these two guys actually dissolve first, and then NH4 here is going to then react with water, right? Because NH4 plus would react with water, and this will be in equilibrium, and I would get back again NH3, right? I would get back NH3 plus, and then my hydroxide ion in this case here. So in this case, our solution, this D solution here is correct, right? Because this here is our correct solution. And again, Br minus here is our common ion, our spectrotator ion. It doesn't really do much here. So I can assume, the Br minus is actually, it's not going to do anything here. Because if I write the net ion equation for this guy here, I can say that this NH4 is going to dissociate, right? NH4 Br minus here would dissociate to form NH4 plus and Br minus, and this Br minus would actually cancel out on both sides here. So this equation here is correct, so which means D here is the correct answer. And I believe that they got the same question as well. The ammonium ion plus the water would give me ammonia and acid here. So this solution here is correct. And again, Br minus here is a spectator ion and is neglected, so they wrote that as well. So the solution here is correct. Good analysis as well. Okay, that was number 5. Number 6 is asking us, is acetic acid a weak or strong acid, and why? Okay, so this number 6 here. Yeah, this number 6, right? Yep. Number 6 is asking us, is acetic acid weak acid or strong acid? So first, let's look at acetic acid. Is either strong or weak. They're asking why. So if we look at the chemical formula for acetic acid, this is the chemical formula. We have CH3 COOH, right? So basically with acetic acids or any basically carboxylic acids, there's a really good rule. And basically you can say that carboxylic acids, or most carboxylic acids, and actually a lot of them, carboxylic acids behave as weak acids. And the reason why is because we have an acetate ion and we have this H plus ion, right? So if I have acetic acid here, and I can draw out my kind of equilibrium here. So CH3COOH is going to react with water to form. Again, I have H3O plus because I know it's a weak acid here, but this here will form I have my acetate ion, so CH3COO minus here. And this here I have a Ka specified for CH3COOH here, and I believe again it's like 1.8 times 10 to the negative 5, I want to say, or that's ethanoic acid. But acetic acid here would be, let's see, yeah, 1.8 times 10 to the negative 5 actually, which is what I said, right? Yeah. So, or 1.76 times 10 to the negative 5, 1.8 times 10 to the negative 5 here. And it's actually a very, very common acid that we use in organic chemistry. And basically, because Ka is less than 1 here, so it's actually going to be a weak acid because Ka here is less than 1, therefore weak acid. It doesn't fully dissociate in water, right? And the difference between strong and weak acids are very, very simple. Strong acids fully dissociate in water. So strong acid would be something like an HCl, right? HCl, if I add water to it, it's going to fully dissociate. It won't go backwards. And I'll form my hydronium ion plus my Cl minus ion, right? This is not a reversible reaction here. Whereas this guy here is reversible depending on concentration, temperature, pressure, volume, all these things as well. So in this case, this here is going to be a weak acid. So acetic acid is my weak acid as defined by this. And why? Because my Ka is less than 1, carboxylic acids will also behave as weak acids, and because they don't fully dissociate in water. So that's the big giveaway here. So Ka is 1.8 times 10 to the negative 5, which means it does not fully dissociate in water here. And so this solution is, I believe it's correct here. Acetic acid, ethanoic acid, it's the same thing. That's good. And this is a weak acid, which they said before. And why? Did they say why? Let's see. I'm trying to scan this, and I don't think they said why here. So, oh, this is our example. So I'm going to say solution here is correct. Acetic acid is a weak acid. And here's an explanation. I don't think they wrote an explanation here, but I'm going to say carboxylic acids. That says, or organic acids are commonly used as weak acids because they do not, or sorry, they do not fully associate. This is a do not. I forgot a do not here. Do not fully dissociate in water. In water, strong acids dissociate fully. Cl, whereas acetic acid does not. And then you can write here CH3 COH plus H2O will be both reacts to form H3O plus CH3 CO minus. So solution here is correct. Okay, that's number 6. Number 7, we're looking at a lot of, oh my gosh, there's a lot of problems here. Okay, I don't know if I can actually do all of them, but maybe I'll just scan the solutions just for the sake of time, or maybe I'll do a couple, or maybe I'll do 1 or 2, and then I'll look at the solutions just to check if they're okay. It says part B, indicate the number of unpaired electrons for the following. It says noble gas, and then NS, and then NP5. Express your number as an integer. Okay, so I have some type of noble gas, and then again, this is the condensed electron configuration. Right? So I have some type of noble gas here. And then it says NS2 and NP5 here, and it's asking us what is the number of the unpaired electrons. Well, if you draw the energy level diagram here, if I have my NS, and where N here is basically our principal quantum number. It has 2, which is good. So this is fully filled. And then I have NP5 here, and these are going to be my NP orbitals, and I have 5. So I have 1, 2, 3, 4, and 5. Now it's asking us to indicate the number of unpaired electrons. So in this case, this electron here is unpaired, right? So this here is 1. So the first question, the answer for the part B is 1. And let's check my answer here. So that's good, right? Choose 1 electron unpaired. That's good. So the solution here is correct. And let me do another one for part C. Part C is this guy here. And they actually use a different approach here. They use spin numbers, and then they said that this here is spin half, so which means this one has to be negative half, which means I have 1 unpaired electron. Either way, both solutions work here. I personally like drawing the energy level diagram, so I can show students which levels are higher in terms of S and P orbitals as well, and it also gets students a habit of what those are. So part C is also asking us again. I have a noble gas here, and then I have, this is NS2, NS2, and then N, and then question mark 1. I don't know what that is. And then D2, or ND2. Oh, I think it's N minus 1. N minus 1, and then D2. Oh, I don't know what this question mark is. It might be a formatting issue here, so I'm going to scroll down to look at this. N1 here. I don't know what this means here. This A here might be a formatting issue. The very, very bad spelling as well. I think it's N minus 1. N minus 1. Yeah. Because it says N minus 1. N minus 1. And then D2. So again, I'm looking at these guys here. I'm looking at N minus 1 D2 here. And it says here, so if I'm looking at my periodic table here, I have, my S2 orbitals are filled, so it's 2 orbitals are filled, and I have D2, right? So it has to be D2 here. So it's either titanium or zirconium in this case here, and it really depends on what integer this N is. If N here was 4, so 4 S2, so let me write down here. If n equals 4, then I can say I have 4s2, and this would be 3d and then 2, right? However, if n equals 5, then I have a different, if n here equals 5, then I can say I have 5s2, and this would be 4d2 here. So it really depends on which, what number is my principal quantum number, and this one, it would relate to two different chemicals, right? So this here is titanium, and this here is zirconium. So this here would be Ti, and this one would be, not Zn, I think it's Zr for zirconium. Yeah, Zr here. So this solution, again, it says here, identify the group of elements, so it's here. So if ns2 is filled, then this could be group 1 or group 2. If n-1d2 group, this is a 4b, or the second row of transition metals. So this here, it would be my transition metals like so. And it really depends if this one is paired or not, if this D2 exists or not. So this solution here is correct because, again, they have group 4b here, which is what these guys are here. And then it's saying if it's just ns2 here, then it's simply just these s2 orbitals. So I'm going to have no unpaired electrons here. So in this case, I don't know if they're asking us, are they asking us unpaired electrons? Oh, no, it's just the group of elements here. So this here is group 4. So the solution here is correct. Okay, I'm not going to do part D, E, F, G, and H. I'm just going to look at the solution to just explain to you what they're doing here, just for the sake of time. Again, I have NS2, this is N-1D2. So it's asking us how many unpaired electrons in this case. So in this case here, I have the first two electrons are unpaired, right? So I can draw this out for you. And it's using the exact same thing as this guy here, right? So I have, again, I'm going to only draw the 3D block here. So I have 5. This is 3D here, and then I have simply 1 and 2, right? So again, these first two electrons will be unpaired, so this one's correct. Part D is correct. Part E here says I have noble gas, NS2, N-1D10, and the NP1, right? So let's look at this block here, and it says I want the group of elements, right? So again, NS2, which means these two are filled, D10, so I have my transition metals are filled as well, and NP1. So in this case, it's relating to group 13, right? This here is P1 here, which is group 13. And as you can see, this is a 3A group, which is the same thing as group 13. So the solution here is correct. Part F is asking us indicate the number of unpaired electrons for, I believe it's probably for the same one here. So in this case, I guess I'll write this one down here. I have, again, some sort of noble gas here. And then I have NS2, N-1D10, and then NP1. So if I'm looking at NP1 here, so let me draw this out. I have NS2 here, N-1D10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then my NP block here would be like something like here, maybe. I don't know, like here. The NP. And this is simply just 1. So I have 1 electron in the P block, which means I have 1 unpaired electron. So this solution here is correct as well. I have 1 electron. So 1 electron here. So they said n equals 1. That's good. And finally, G and H is the exact same thing. So it says identify the elements that correspond to this group here. So I have, let me write this down. Noble gas is NS2, and this is -2 now, and then F6 here. So I'm in the F block now. So this is what, so my lanthanides are my actinides are my F blocks here. So this here would be a, this here is a 4F block, and this here is a 5F block here. So again, I'm looking at F6 here. So 1, 2, 3, 4, 5, and 6. So it'd be in this category here. And this here would be, the elements here are SM and PU. And these two are my elements here. And I don't think they actually wrote that down here. So I'm going to write SM and PU for that solution for part, this is for part G. Elements are SM and PU. And then for part H here, it's looking at, okay, how many electrons are filled here. So I can go and draw my energy level diagram again. And as you can see, F6 here is, I have, the block here is very, 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 very long. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15 here. In this case here, I have it's an F6, right? So this here would be six pair of unpaired electrons because F block is 18 electrons long. So you can say some type of n minus 2 F block. It was 1, 2, 3, 4, 5, 6, 7, 8, and then 9 here. So 9, because I have 18 electrons in total, and then I only have 6. So I have 1, 2, 3, 4, 5, and 6 here. So again, in this case here, I have 6 electrons that will be unpaired here. 6 electrons here. And as you can see, this one's correct. 6 electrons are unpaired. So I'm going to say part G, elements are S, M, and Pu for this guy here. For the electron configuration as follows. So noble gas here, I'm going to write this here is minus 2, F6 here. So the solution, depending if n would equal 6 or if n here equals 7. So solution is correct for the most part, but I'm just going to correct that one part. So solution is mostly correct. One correction. So all other parts are correct. So I'm just going to say it's correct for the sake of this question here. Very long question that they're giving us here. That was number 7. Let's look at, maybe we can do 2 more for today. This is number 8. It says a 6.55 sample of aniline was combusted in a bomb calorimeter. If the temperature rose by 32.9 degrees Celsius, use the information to determine the heat capacity of the calorimeter. So I'm going to draw out the chemical equation here. So I have 4C6H5NH2 plus 35O2. I guess I'll put the states as well. This is liquid here would give me, this is a combustion reaction, 24 CO2 in gas plus 14 H2O in gas plus 4 NO2 in gas as well. Okay, so let me zoom out. So I have this this kind of equation here, and then my delta H. I'm gonna my enthalpy of my reaction here is negative 1.28 times 10 to the 4 kilojoules. Okay, so it's asking us if the temperature rose by 32.9, use the information to determine the heat capacity of the heat. The heat capacity of the calorimeter. So what we're doing here is first we have to figure out, again, we're given our sample of aniline here, and this is 6.55 grams, right? So this here is 6.55 grams, and this here is the mass. So which means, and I'm given the molar mass of aniline as well, which is 93.13 grams per mole. So instinctively, I'm going to basically solve for the moles, right? So let's solve for the moles first. So moles, again, I know it's mass over molar mass. So this here is 6.55 grams divided by 93.13 grams per mole. And this will give us our moles of our aniline here. So 6.55 divided by 93.13 will give us a value of 0.070 here. So I have here, this is 0. There we go. 0.070 moles here. I'm going to erase this just for the sake of time, for the sake of space actually. 0.070. And after calculating the moles, what we can do is actually calculate our molar enthalpy of this reaction, right? So we know that our reaction here gives us, again, a negative 1.28 times 10 to the 4 kilojoules. So what we can solve for now is we can solve for basically how much energy is being released here, right? So again, we can say that per mole of aniline here. So because again, I have 0.07 moles and I have 4 of these guys here, I'm gonna have to multiply this number by 4, right, to give us our per mole ratio for this guy here. So this would be 0.28 moles, I believe. Multiply that by 4. Let me check that on my calculator. Yeah, 0.2813, I believe. But I'll just say 0.28 for now. And with this is in moles, again, this is I have this is in our kilojoules. So what I can do now is I can actually solve for how many kilojoules are released per mole of aniline here, because this is the reaction, the delta H of the entire reaction, right? So I can say here the molar enthalpy, or delta H here, would equal delta H of the reaction divided by our moles, right? And this here is going to be, I have negative 1.28, or in this case it's simply just positive 1.28 here. Actually, no, I'm including the negative here, sorry. 1.28 times 10 to the 4 kilojoules divided by, this one would be, I have 0.28 here. 28, maybe I'll take it a couple more decimal places for us here. 2813 moles here. And these moles are going to cancel out actually, because I have moles and moles here. So it's actually just going to be 0.2813. And then you can say, I guess I could say, yeah, because these units are going to cancel out. And then I'm going to get a value of, this here would be, see, negative 1.28 times 10 to the 4 divided by 0.2813, the value of negative, let's see here, I get a value of, yeah, 10 to the 4 kilojoules divided by 0. I think, what is up here? 0.07. Sorry, give me a second here. 1.28 times 10 to the 4 divided by 4 times 0.07 give me 224 here. So this, so I think I mixed up my steps here. So this, so what I have here first is I'm going to, or what they did here is actually they divided the heat of reaction by the amount of moles to figure out how much energy is being released per mole of the reaction here. So I have negative 1.828 times 10 to the negative 4 kilojoules. I'm going to divide that by 4 moles here first. So that's going to give us some value per mole of oh sorry, that's positive 4 per mole of aniline here. So let's see, per mole of aniline. So here's 4 divided by 4 here, which is simply negative 3,200 kilojoules per mole. And now what I can do is I can actually multiply this number, because this is in molar enthalpy now, right? So I can say, and I know that delta H equals the molar enthalpy times the delta H of our of the reaction here. So I can say, or sorry, not the this would be delta H divided by moles here. And what we have here is we have negative 3,200 here. I'm going to multiply that by our moles, which is 0.07 would equal our delta H. So this step is not this step was required, but they basically did it in the they changed the energy first, and they didn't have to multiply that as well. So this would give us a value of times 0.07 of negative 224 here. So delta H here would be negative 224 kilojoules. And then basically if I want to find the heat capacity, I know that Q equals MC delta T, right? Q equals MC delta T. My Q here is negative 224 kilojoules. And it's going to equal the mass here, which is, let me scroll up here. The mass here is 6.55 grams times C. I don't know C. I'm trying to solve for C. And the delta T here is 32.9. It rose by 32.9. So this here would be 32.9, right? And then I'm going to basically algebraically solve for my C here. So I'm going to divide both sides by 6.55. So let me see here. By 6.55 would give me a value of this negative 37.2519 equals 32.9 times C. Divide that by 32.9, and this will give us a value of negative 1.9 0.13 kilojoules, which is not correct here because they got 6.84. So I'm just thinking about the math here. Heat capacity equals total amount of heat divided by temperature change. So let me write that down for us here. So it's asking us C here equals Q over delta T, but they're missing the mass here. So this solution here is incorrect because they didn't actually include the mass of our aniline here. So this solution here is incorrect. So I'm going to continue with my solution here. C is going to equal, and it can't, specific heat capacity can't be negative, so I'm going to take the absolute value of this here. So this is actually 1.13 here, and this is going to be, let me just work on my units here. So if this is in kilojoules, it's going to equals grams times C here. So if I want kilojoules in this case here, so I have kg here, I have grams and C here. So we multiply that by kilojoules over grams times C. So this is kilojoules over grams times Celsius here is going to be my heat capacity for aniline here. So this here is my answer. And this solution here is incorrect. Solution is incorrect. And then I'm going to copy and paste here. This is a wrong solution, right? So Q equals MC, MC times delta T. So therefore C would equal, I have Q divided by M dt here, T, which would equal, Q here is negative, again, or 225 kilojoules divided by the mass here, which was 6.55 grams times 32.9 degrees Celsius. And this would equal 1.13 kilojoules, sorry, kj over grams C. And this here is our solution for this problem here. So again, thank you so much for watching this live stream. That's going to be all for today because I finished about 8 problems. I don't think you finished another problem within this live stream, but thank you so much for tuning in. Again, if you like these live streams and videos, definitely check out the OneClass YouTube channel at youtube.com/OneClass. You can find all the pre-recorded videos there, and you can come and check my videos out. Again, my name is Joey. I stream on Monday to Friday. Monday, Wednesdays, and Fridays are math problems, and Tuesdays and Thursdays are my chemistry days as well. So again, thank you so much for watching. Again, stay safe, stay healthy, have a great day. Take care.